check my factoring, guys, make sure that's factored into what, does it or not? 2x squared minus 5x plus 2, of course not. So it's minus 2 here. And minus 1 here. Then we'll check it out.
The denominator also factors.
It does factor, yeah, I think that numerator out, I think that numerator he gave me does factor, I think, I see the factors are correct this time. Yeah, this is the difference of squares, see why I placed this on the handout. See why I placed it on the handout. What happens on this one that maybe did not happen yesterday? Do I have a factor canceling out?
Yeah, x minus 2.
Now, as soon as you see a factor canceling out, in other words, to simplify this, those two cancel. Guys, quickly, that indicates, that is an indicator that when you graph this, you're gonna have a hole on the graph. The graph's gonna have a hole on it. Now, where's that hole located? And we want to point coordinates. Well, you can take the factor that canceled, which was x minus 2 in my case, and solve it. And you'll see where the x is. The x is 2. Okay, I need y also because I need to plot that and show the hole is there. So guys, out to up where or down where? And I think Jonathan, you and I and Chris and others who were down in the room there earlier, do you recall how we find the y coordinate?
Just plug in the 2.
Yeah, plug in the 2 back into this simplified version. And get the y coordinate. So if I replace x by 2 on top there, guys, yeah, what is that, 3?
Yep.
And it's over, what is it, 4?
Yeah.
So that's the location of the hole on the graph when I finally get to it.
Sorry, what do you plug in for the hole?
Yeah, you go back to
You
your
plug in the factor that you canceled.
Yeah, the simplified version looks like this. Alright, that's the way the simplified version looks. And I went back to that simplified version in the orange and replaced x by 2. We got 3/4. Okay, that's the location of the hole. Now we got that done, but you're telling me step 1, I've cleaned up first. You said though step 1 was asking for the domain.
Yeah.
Okay, so the domain quickly, guys, here is, I'll take this, x cannot be equal to plus and minus 2.
Yeah.
Now, can someone tell me, be clever? There's a different reason for each one of those. X cannot be a 2, x cannot be a negative 2, and they're can't be used for different reasons. Anyone tell me, let's say x cannot be a 2, why?
Because of the hole.
Then you got a hole there.
And then negative 2 is because of the vertical.
And negative 2 is going to give me probably, right here, a vertical asymptote. So the negative 2, when I start graphing, you'll find a vertical asymptote of negative 2, so that I can't touch it. And all of a sudden, I can't use this either, the hole, which has x to be a 2. Okay, so make sure you see that. As long as you do that for me, I'm happy for the domain. Jonathan, I think step 2 was just to write that simplified version down.
Yeah. Simplify, right r, that's in the lowest terms.
2x minus 1 over x plus 2, right?
Yep.
Okay. Now, what was next?
It says, name the intercepts x, and y of the graph.
We got to find those. Very lengthy. Okay, the x-intercept, guys, merely replace r of x by 0. Now, we did this yesterday, and I'm going to go to my simplified version, which is this. Get all this to work out for me. This was the simplified version. So we set that equal 0 and try to solve. Guys, if I do a cross multiplication or merely use a denominator, am I going to merely end up with 2x minus 1 is equal to 0?
And then x is equal to 1.
Here's 1/2, so I'll mark that with an ordered pair as 1/2 0, that's my x-intercept. There's no mistake, let's hope not. Y-intercept a little bit easier. You go back and find r at 0. Replace all these in the simplified version, all the x's by 0. Guys, if I go back to the orange and put a 0 in there, I'm going to end up with
Negative 1 over 2.
negative 1 over 2. So this is going to be my y-intercept. Now watch carefully, I'm so glad we're all here today. Because one little mistake on the steps here that I'm going through may throw the graph off by the time I get to the graph. So far, so good.
Yeah.
Jonathan, what was step, I guess step 3 coming up? Or step 4?
Determine the vertical asymptotes.
Easily done. I go to my simplified version, look at that denominator. I think I said on the handout, set that denominator equal to 0.
Yep.
So that merely says this, and you're going to end up with that. Yes?
When we're looking for horizontal asymptotes.
Oh, we're not there yet. Hang on. Hang on. We've got the vertical out of the way. Now, what's the next one?
So then it says determine the horizontal asymptote of any.
Abbreviate. Now, this is where I'm going to just jump in and give you some rules, not use the specific reason behind it. I think I pointed out one rule yesterday. If you're lucky, the best thing to happen is if the degree in that original function is the same on the top and the bottom. The degree on top is 2, the highest exponent. And is the highest exponent the same thing on the bottom denominator? If that happens, quickly, this says, find that, 2 over 1, those coefficients, and then we'll tell you the location of that horizontal line. So right quickly, that would be y is equal to 2 over 1, which is nearly 2.
And then since we found f of 2 as a whole, what does that mean?
We'll see,
potential
we'll
crossover
see,
points?
we'll see. Now, I got that. Now, there could be a crossover point. Okay, so I'll have all this typed up for you. So you got a horizontal asymptote at 2. Now you're asking yourself, Professor, might the graph cross over? Because sometimes it will. So let's try to find if that's happening here, is there a crossover point? Does anyone recall how to find a crossover point if there is one?
Set it equal to.
Set the 2
Oh,
equal to, I would use the simplified version, set equal to the function. You're trying to see if the function and 2 have something in common. So you set them equal to one another, and see if they have something in common. So we'll set 2, the red, equal to this in the orange, my function. And if I do a quick cross multiplication, I mean quick, you end up with this, that's no issue there. But guess what happens? I'm trying to solve for x. What's going to happen in this case if I attempt to solve for x?
Still cancel.
These cancel, which tells you you can't solve for x, therefore there is no crossover point on this graph. Retry it, there is none. Jonathan, remind the class what this next step is.
Well, it says determine the oblique asymptote of
Okay,
any.
we gotta stop there, this one does not have an oblique. Okay, guys? So we got all the detail. Now this is the one type that you'd love to see on that test. Because it doesn't take too much here on this test. Park, I don't know where my straight edge went. Someone took it. It's not over there, is it? No.
I couldn't check the first floor. I couldn't open it.
You couldn't open it?
Yeah.
Oh, you mean the rooms?
Yeah. The first,
He's not down there to open it for you?
I didn't have. I'll ask.
Okay.
Yeah.
I may have left it, I don't, anyone with me in that room yesterday, did anyone
I think
remember
you
my
did.
stood up?
It was at the whiteboard, yeah.
Yeah.
Oh, it's down there then. You can't get in that room?
I'll ask.
Go ask him.
Yeah.
Yeah. Would you please?
Yeah, sure.
Geez, I'm getting nervous. I gotta have that straight edge. Okay.
He
Guys?
knows the math lab.
In the math lab? Hey, does he know? I think
I
it
don't
is.
know if he caught that, but.
He'll find out. I hope. Please. Okay. Do we have enough now to graph this? Okay,
Yes.
now here we go, guys. To place all this on here, what does this graph look like? And of course, I might do it like this. Now, it's up to you as to what you want to put first. I usually go back and pick up the intercepts first. So guys, we got x-intercept, one x-intercept at 1/2. Let me mark that. Mark this in bright red. So place one here for a reference, and mark right here, this is 1/2. And a y-intercept was down -1/2, so we put a reference of a -1. Right here is the y-intercept, -1/2. As I look further in my information here, I see there's a vertical asymptote at -2 if we have no mistake. So we'll go over to a -2 and show this. A vertical asymptote. The partial credit, tons of partial credit here. Horizontal's up at 2, that 2 is playing a big part on this one. Okay, let's go up to 2. And show there's a horizontal asymptote up there. Like a ceiling. Jonathan, I think you used that word. Crossover point none. Now, do we have every, oh, by the way, there's a hole on the graph. And we said the hole on the graph eventually ended up, where was it? Out 2, up 3/4. Okay, so out 2, up 3/4, and we plot that. We'll do it out here. And out 2, up 3/4, let's say it's close to 1. Right in there's a hole. Well, I should actually label it, make sure. Out 2, up 3/4. Now, I have all the detail on the grid. Can I graph it? But first, can anyone tell me how many pieces to this graph are there?
I think we're looking at.
How many pieces? There's something to the left of that vertical asymptote. By the way, how many vertical asymptotes do I have here? Only one. So there's something happening to the left, something happening to the right. There's only 2 pieces. Now, if you want to start on the left, and I see on the left, I have no points to work with. You can plot points. Form a table and plot points. Or you can say, no, Professor, I think I see what's happening over there, even though I have no points. And does anyone have a guess as to, if I do look at the left, what might the left look like?
I think it would be above the red, or above the
black?
horizontal and to the left of the.
You mean like this?
vertical. Yeah, because there's no x-intercepts, it's picking
You can, Professor, to follow those asymptotes,
or crossover points.
you have no choice.
There.
It's not in there.
Yeah, it's not.
In the room where I was.
Yes, first floor, 106.
Did you check with him? Maybe someone turned it in. Did you check, is he down there?
The manager's gone, so there's a studio worker, and I opened it.
Okay, I'm getting nervous. Okay. Is that true, guys? Does it have to be there? On the left. Has to be. And I know, if I did this, don't do this though. If I did this, you say, wait, Professor, this follows the black and follows the blue. It follows those asymptotes. But, just like Eric just told me, that one crosses the x-axis. And there is no x-intercept there. I didn't mark an x-intercept there, so I can't use that one. Even though it does follow the asymptotes. Now, so something's happened on the right. I've got lots of things to work with on the right. I've got to pick that point up, pick this point up, go through and, or it's cross over this, and show there's a hole there. Follow the black, follow the blue. I don't think I have much choice. When I connect to do that, here's the blue vertical. Can't touch it, get close to it if you wish. It's gotta come up, pick up this, come on up, pick up that. Come on up. Of course, or jump across there and continue on its way toward that black horizontal asymptote. If I see that much right there, I'm happy for the graph. Hang on. Are we okay right there at that point?
Yeah.
So this is the first one I think I've done, or I may have done a simple one, yes, there was a hole on the graph. There it is, guys, that's the way it looks. Leo, what was that question?
Sorry, how did you get the 3/4 for the whole?
Yeah, you gotta take the, we got the 2. Right. Back here, or what, yeah, 2. So I had set the 2 equal to the function.
Right.
And I cross multiplied and I found there's no crossover point there. But you're saying back here on the 3/4, how to get that?
Oh, I didn't see that.
Yeah, there's a hole here, we've got x be a two.
Oh, wait, no, you're plugging in f
I
of
plugged
two,
it right here.
not?
I plug in two into that orange.
Okay, yeah, yeah.
That's a simplified version of the function. In other words, Leo, good question here. I found this, I found f, I call it r. I found r of two.
Oh, okay.
Pretty super, right there, and just plug it
And
in.
the hole exists because two of the factors cancel.
That's how I got 3/4.
Oh, thank you.
Now, the graph is done, but we got so much to do here tonight, guys. Yeah, Eric?
So does the hole, in terms of the domain, is it basically the same as an asymptote?
Yeah, because we
Would it
already
be-
said the domain x cannot be a positive, negative two, positive two.
So
It
it's
can't be a negative
infinity
two,
up to
because
negative
vertical.
two.
It can't be a positive two, because there's a hole there.
So it would be negative infinity up to negative two.
Oh, and that,
union-
we're gonna put it in interval notation. Yeah. And there's the graph. How's it look? That's not too bad, is it? You haven't seen one with an oblique yet. Okay. Okay. Step back and look at it. I think it's cute. There it is. Now, if you want to put the domain and the range and all that business here we go. I gotta be careful now. Eric, I heard what you said. You said, Professor, after the graph is done, you usually ask for the domain, which we've already said the domain back here was, x cannot be, what was it? Two or negative two. So he says, based on the graph, if that's true, then you're gonna write like this.
Union negative two, two.
Absolutely.
So in terms of the domain, you can basically treat a hole like an asymptote.
Absolutely.
Okay, sweet.
So that's just another way to say what we said earlier, the domain. Now the range, be careful, may throw you, that's the up and down.
But the hole also affects the.
There you go, that messes me up. So guys, let's start at the bottom and go up. I see it's dropping down forever. So it's negative infinity. Now it starts rising, and what's gonna throw me off a little bit here, it goes right there, and that y coordinate at that hole cannot be used. So it's a negative infinity up to what?
3/4.
3/4. Look at the y's here. Then union, then you jump across it because it continues. And guys, what was that little piece there that continues for the y's?
2.
That's from 3/4 up to what? 2.
And then 2 to infinity.
Okay, and we had no crossover point there, thank goodness. And then jumped across up there from 2 to infinity. We call that madness. That's madness. And that tells me the range on this graph. All that makes sense? Okay, because I have only one more of these are so lengthy. Okay. Now, if all that's true, on the side here, I'll have questions like, let's say this, guys. Find the limit as x approaches infinity of this function. So based on my graph, it says take a hold of this orange graph, you're going this way forever. On the x-axis, you're pulling the orange graph along with you. How's that orange graph behaving? What's it doing? Is it going up and up close to 2? It'll never get there. That's why they call it a limit. So it is approaching 2. If I try the other end, this is like in behavior, limit as x is approaching negative infinity of that function. Now you're out here on this side, taking it this direction forever. So if you pull that orange graph to forever to the left, is it also approaching, we'll never get there, the black horizontal asymptote, which is 2 again. Making sense?
Yes.
That's the word limit right there. Number 2. By the way, by the time you get to math 7, they're going to ask you to use an epsilon delta, those are just letters they use, to they'll tell you how close they want to get up there. And you got to find the interval that makes that happen. What numbers can I plug in there? They may say, keep taking this out, Ramsey. But I don't want you to stop until you're within 0.0001 of 2. You're that close to 2. Now find me an appropriate x that will make that happen. Don't go there yet. Let's do the math 7. Number two, let's find this limit. Limit, as x is approaching, let's approach -2, my vertical asymptote, and start from the right, on the right-hand side. So guys, that positive sign says stay on the right. This is the piece of my graph that's on the right of -2. Now all I want is a description of the behavior. What's it doing? Is it dropping down through negative infinity? It's, so, here, negative infinity. On the other side, limit as x is approaching -2 from the right. Now you're on the right-hand side of -2, and the orange graph, of course, is this. It's close to a -2, but it's on the right. And how would you describe what it's doing? Rising through positive infinity.
Sorry,
Wait, they're both the
from
same.
the left.
Okay, from the left, right? One of them, they're both positive.
Oh, right. So, I'm trying to read. That's from the left. With me, guys? On both ends? Jeez, this could be the test. This could be 75 points, just one problem. It won't happen like that, but it could be. And I'm sure there's tons of other things I could throw in there, like where is r of x less than 0, where is r of x greater than 0? You guys look at the graph and see when it's above, below. I could do tons of things. Okay, the graph's done. I got one more to do, and please watch carefully on the next one. It says sketch of part B. Here goes. Jonathan, tell us what it is. Last one.
Oh, last one, r of x equals, x squared minus x minus 12 over x plus 1.
Now, the first thing you're gonna do when you get your test next Friday is to check and say, is Professor Brandon being nice to me today or not? You're gonna be checking out the degree on the top is 2, highest exponent. The degree in my denominator is 1. They do not match up to be the same number as this one. That says no, you don't have a horizontal asymptote this time. Like I did on the last one, they did not match up. Now, if I take a close look at what I do have in front of me, they're not the same. The top one's 2, the bottom one's 1 for the exponent's degree. Is the one on top exactly 1 larger? If it's exactly 1 larger, you have now a new asymptote. You don't have enough to worry about. And a new name. It's not horizontal, it's not vertical. You will now have on this graph, when I get to the graph, you'll have something called an oblique asymptote. An oblique asymptote. Not a horizontal line, not a vertical. You'll have something like this. A slant. In fact, some textbooks call it a slant asymptote. The line is slanted. And that's going to serve as an asymptote, which is going to be very strange to have an asymptote slanted. Now, where's the location? Back here on my horizontal, I did the little routine that we always do, and I found on the horizontal, here it was merely, as these matched up, was 2 over 1.
Does P2 over P1 determine the
Hang
slope
on.
in this
It's
case?
2 over 1, wasn't it? Yeah. Can't do it here. I wish I could. I wish you could just go and say, Professor, it's 1 over 1. There's leading coefficients. It's not, because this one is not horizontal, it's oblique. Now watch carefully what I gotta do to find it. David, ask that question.
Does it matter if the degrees are on top or not?
Beautiful, it does. I'll show you the other case. Now this one, the degree on top is exactly 1 larger. There are some out there where the degree on top could be 2 larger. Now, I'm not going there. It can happen. Just out of curiosity, suppose the one on top is 2 larger than the one on the bottom. you have an x cubed on top. I still just have a single x on the bottom. Does anyone think they know what type of an asymptote?
Parabola.
A parabola. Not, the parabola's not the graph. The parabola is an asymptote. It's giving guidance to the graph. Thank goodness we're gonna stick with in this course, but get ready in case you ever see it. We're gonna stick with, for me, for this course, linear. I'm not going into the quadratics and the parabolas as asymptotes. I'm gonna stick with the linear, okay? So we're gonna call them oblique. How do we do it? Guys, it's unique. To find where that oblique asymptote is, it's gonna require me to do this. And this is where we need to make a trip across the street. You gotta do long division. Now please tell me, the reason I'm doing long division is, I know and you know, if the oblique asymptote for us is gonna be a straight line, slanted, I know a straight line has always a form that looks like this. And therefore I'm gonna try to find a form that looks like that. And what it takes to find that form in this case is, you gotta do long division. Now we may have forgotten how to divide. It's been a long time, I guess, that you actually have done a division. So let me do this on the side here. If I were asked to do this, back then, remember doing this, guys, when y'all smiled and teachers smiled? I've walked on some campuses, I told you I used to supervise teachers. I'd walk on some of these campuses where those teachers were located, everybody smiling, and I said, this is the best school ever. Oh my goodness, teachers smiling, students are smiling, everyone's so happy. Oh. Then I checked on the scores. Oh. I don't know where those smiles were coming from, but I saw some smiles, but those scores didn't look too smiley. Long division. What'd you do first back then? You asked yourself, how many times will 12 go into 50? I hope. In this case, what, 4? And 4 times 12 is what, 48? You ever doing this? What did we do next? We subtracted. 50 subtract 48 leaves me right now 2. You bring down your next term, which is 3, and you start dividing again. Now how many times will 12 go into 23? 1. And then 1 times 12, much like the synthetic we were doing here. 1 times 12 is 12, that goes here, and then you subtract again, and I think you're going to end up with 23 subtract 12 leaves you what, 11? And that was known as this back then. A remainder. Oh my gosh, you guys have been out of kindergarten too long. They taught this back in kindergarten. Maybe first grade.
Second grade.
You've been out too long. Now, this was my divisor. They call this divisor. Inside here was the dividend. Just some vocabulary. On top, quotient. So you got a divisor, dividend, quotient, and then in fact I also have a remainder. Now, I have to apply that process on this. Now, maybe a little bit easier since we're accustomed to algebra rather than numbers. Here we go. To go back to this to find out my long division, first thing you're going to ask yourself is, how many times will x go into x squared?
2.
Okay, now what I'm citing, x squared divided by x. What is that? That's x. Is x squared being divided by x? That's your first term in my quotient. Then what did I do back here after you found the 4 back in kindergarten? 4 times 12? I gotta do that business. In this case, it's x times this divisor. So guys, x times x plus 1, like a distributive property, will give me
X squared plus
x squared plus x. Then what did I do back here after I got the 48? I subtracted. Someone said 50 subtract 48, Professor, I will. Here I got to subtract also. Now if I subtract these two guys, that's like a sign change. I put it in orange. Subtract means change the sign. The first two terms will drop out, which I'm glad they did. The x's though will combine to a negative 2x. That's like me down here now, 23. In the elementary school problem. What am I gonna do next, guys? I take x into a negative 2x. Process continues. What about x into a negative 2x? What's gonna happen? Will the x's cancel? X into a negative 2x and leave me what? Y, of course. Right here is what it says to do. It says x into 2x, a negative 2x. Looks like this. That's what this means. Takes this into this. X is canceled. You're left with a negative 2. That's my next part on my quotient. Up here. Now, that's like me calling this a 1 on this one. What did I do next? I took 1 times 12. And I think that's where that 12 came from. Here, in this case, I'm gonna take negative 2 times x plus 1. Guys, negative 2 times x plus 1, distributive property will be a negative 2x minus 2. Subtract, and for us, subtract means just merely change signs down here. So change this to a plus, change this to a plus. These two will drop out, and I'm left with, looks like a remainder of 2. Now, one nice thing about this, if there's anything nice at all on this long division for us, is this is gonna play no part in what I'm looking for. I'm looking for something that looks like this, for a straight line. Is this on top right now in the mx plus b form?
Yes.
I don't have to look at this remainder down here. Is x minus 2, could it take the form of a straight line,
Yes.
mx plus b right now? So my oblique asymptote, when I get to the grid, I gotta graph x minus 2. I can do it by x-intercept, y-intercept. I can do it with slope, y-intercept. Anyway, you guys know how to graph a straight line, graph it, but that's gonna be my asymptote. Wow. Now, the next question. Whew. It can happen, very seldom does it happen for us. On the horizontal, could there be a crossover point? There could be a crossover point on this thing.
Yes.
I'm not gonna check this one, I don't think there is, so we'll look at it closely. I don't think there is, so we're not gonna worry about that for right now. But there's a possibility of a crossover point on the oblique. The graph will actually cross over the oblique at times. Now, I'm gonna check the crossover point here, guys. I'll let you guys know, just to save you a little time here. So we got the oblique with the asymptote. Now, number 2, since I want to graph this completely, geez, I need the other details. I need the intercepts. I need a vertical asymptote. So Jonathan, I'm gonna pick up, as we did on this row here, I need to pick up x-intercept and y-intercept if they exist. Because I need these because I want to graph this completely. X-intercept merely set the what? This equal to 0. Now, if you want to factor this first, go for it. I think the factors. Is that x minus 4, x plus 3?
Yes.
I think. Over x plus 1. Thank goodness no factor cancels, so this thing does not have a hole on it. Don't have to worry about the hole on the graph here. Okay, set that equal to 0 and find the x-intercept, and you will have this. As I told you yesterday, one of my former students told me to find this, professor, it merely comes down to setting the numerator equal to 0. If you do a little quick cross multiplication, he was telling me just go ahead and do this. Just set the numerator equal to 0, and that's all you need to find the x-intercept. If I do, split this up, quickly see x is 4. So guys, that's 4, 0. And this one, set this equal to 0. You're going to end up with negative 3. So negative 3, 0. Now I got the x-intercept done. I've got 2 of those. I've got the asymptote, which is going to look strange, it's oblique. Y-intercept, always, we'll find r at 0. Go back and replace all the x's by 0. You may do that here if you wish. If you do, you're going to end up with a negative 12 over 1.
Over negative, oh shoot.
Negative 12 over 1, which I think is negative 12. label that like that. You guys agree? All that, look at that, tons of partial credit. So if, out of 75 points, the one question about a rational function could be easily 18 points of the 75. Okay, John, remind me, what else do we usually find before we start graphing? We got the intercept, we have the asymptote, what else?
So, it just says,
Well, what else we usually find? We found it over there, what else do I need?
the domain,
All right, later
oh,
on.
the vertical asymptotes.
Vertical, let's
Yeah,
get the
the
vertical.
asymptotes. And horizontal asymptotes.
Absolutely. And there are no horizontals here. You can't have an oblique and a horizontal.
Oh, yeah.
Okay, vertical easily done, set that denominator equal to 0, that's the routine. And here's the location of my vertical asymptote. I think we have enough now to go to the grid and try to put this together. Now, don't be upset, don't get nervous, this is the first time you've seen an oblique, so bear with me. I got to put all this on a grid and hope for the best. Guys, I hope you can see it from over here, if I'm over here. I can here. We got the x-axis. We'll find the y-axis here. Let me step back and together, that's good enough. Now, let's start putting things together. I don't care what you put on there first. I usually put the intercepts, but it's up to you. The x-intercepts were, there's two of them, out 4. You label and mark right here. There's an x-intercept, also a -3, x-intercept. Y-intercept, oh my goodness, way down here at -12, guys, we'll just drop down here and mark it. And show it's down here. Let me pick up my vertical asymptote next, get that out of the way. That's a vertical asymptote located at, looks like it's -1 if we have no mistake. So it's right in here somewhere. Looks like that. What's the only thing left to put on there? The oblique. I got to put the oblique asymptote on there. And the oblique asymptote has a name of this. I like to graph this. Now, if you want to find the x and y intercept of that red and plot those 2 points, connect them, that will give you the straight line I'm looking for. Or if you want to use the slope intercept method, use slope in trying to graph it, go for it. Guys, I'm going to just quickly, let's look at it. Is the x-intercept for x minus 2, 2?
Yes.
So I'll go down and mark that here shortly. Where's the y-intercept?
-2.
-2, I think that's the fastest. Let me go in here, guys, I'm gonna put it in orange here. X-intercept is out at 2. Now, this is for the oblique. And the y-intercept, you guys told me was down here at -2, let me mark that right here. There. 2, -2. Connect it. Yes, it's gonna be a slanted line, and it goes like that. Now that is my asymptote. That's what serves as an asymptote. Let me step back. Can you guys see all? Can you see that? Everyone see that? Okay. Now, I need to graph it. Does anyone have in mind, first, how many sections to this graph will there be? How many sections? Shame on you.
Oh no, 2, because of the vertical asymptote.
Yeah, how many vertical asymptotes do I have? One. I have one vertical asymptote staring at me. There should be something to the left of it and something to the right of it. Now, does anyone have an idea? I'll take your question here shortly. Does anyone have an idea of what on the left, because I gotta take this point up here, to the left of the red vertical asymptote, and I gotta follow the vertical and I gotta follow this strange orange. I gotta follow both. Both are asymptotes. And I'm assuming I'm not gonna cross either one. Does anyone have an idea what the shape may look like? Leo says he does. Describe it for me.
Is it gonna just be like a wider curve that goes through the x-axis?
Yeah, I think so, right?
So you're saying maybe it looks like this, picks that point up, and then follows that orange.
Yes.
Yeah.
That's why those asymptotes are there. That's a quick sketch of what the graph looks like. I didn't plot any points to see how close to the asymptotes they are, but basically that's the shape. Now on the right of the red vertical, there's another section. Well, there you gotta pick up this point, you gotta pick up this point. And you gotta make the graph follow the orange and the red. I have no choice. If I wanna follow the red and the orange and pick up those 2 points, I have no choice. There's the other piece. And there's your first example of what they call an oblique asymptote. David?
So you can touch the oblique asymptote?
Now, well, yeah, I've seen some where you can. I'm gonna stay away from those, okay? I've seen, just like on horizontal, you can cross the horizontal, have a crossover point. There could be a crossover point. That black graph could eventually go out here somewhere and cross over and hover over it. It'll stay close to the orange. That's right on top of it. And it hovers around it on top. I usually don't let that happen, but things can happen. Eric?
How do these oblique asymptotes like translate into a limit?
Okay, I got you, hang on, I got you.
For the long division, are we just going until we find something that resembles the mx plus b?
Break it down.
So like when we're doing the long division for part 1,
Yeah.
are we just going until our quotient looks something like mx plus b?
Always. Leo, a good point. As soon as you see this right here, you're doing your long division, you say, as soon as you see it's an mx plus b form up there, you can stop. You don't have to go all the way down and find what that remainder is. No, as soon as you see mx plus b coming out, that's what I'm looking for, the line, straight line. So as soon as you see mx plus b, which will give me a straight line, you can stop. You don't have to worry about the rest of the long division. You don't have to worry about the remainder until you go to grad school and that remainder tells you something else. We're not in grad school yet, so just stop. Got it.
So then can we assume that we're only ever gonna get 1 degree of quickness in problems?
Beautiful, beautiful. I'm sticking with only where the top is exactly 1 larger, not 2 larger, not 3 larger. The top exponent is exactly 1, which forces this into be a linear asymptote. Good question. I'm not, your textbook, I think, does try a few where they go higher.
Where did you get y equals -2? Where did that -2 come from?
Okay, I gotta find where I am first.
Because like the y-intercept that was -12 on that end, but you said it was the.
Oh, yeah, the y-intercept on the asymptote replaces x by 0,
so-
not on the graph, on the asymptote.
So it was 2 and,
Yeah, I'm talking about a y-intercept on the asymptote, and also there's a y-intercept on the function.
got it, y-intercept on function.
There you go.
Okay, y-intercept.
Okay, guys, let's look good. And that's the first one, that'll probably be the only one I can do, concerning, an oblique asymptote. And before I close it down, you cannot have an oblique and a horizontal at the same time. Cannot. Okay? Woo, let me step back and look at it, it looks nice, I think. Looks good. Now, here's some questions here. Eric, here we go. After you get all this done, and you're pretty well satisfied, your graph looks pretty good. Number 1, let's try limits. Limit as x is approaching infinity, that's like in behavior, of this function. And I have the function graphed in black. Anyone tell me, as you go on the x-axis, you start going this way, I stopped at 4, but you continue all the way down, and you're dragging that black graph along with you. Where's the black graph going as you pull it to the right forever? And pull the black graph, what's the black graph, how's it behaving?
You want first opinion?
I'll take that.
Or,
Hang on. I'll take something else.
Could you say x minus 2?
Is it also getting closer and closer and closer to the orange oblique? Okay, I think your textbook says infinity like Johnson did. It's also rising forever, but really, so you're getting closer and closer and closer to the oblique. Okay, Mr. Park.
Mm-hmm.
Okay, hang on. Park, do me a favor.
Mm-hmm.
I'm gonna go way out there. I'll stop at 4. On the x-axis, I'm gonna go out to, here we go, Park. I'm gonna ask my students to find this value. Let me point out right now. Are at, why not, 525. Most students would think, well, he wants me to go back, I know how he is, and replace all these x's by 525. That's what it means, plug in 525, crunch it out, and some probably would even go back here and put it in. And crunch it out, and crunch, and crunch, and crunch, right? Someone tell me something about R at 525.
What's positive?
I'll take that, something else.
But well, that's what I said.
R at 525, where I stopped at 4, 525, here that way down the street, on down through there at 525, and that graph is still there. What's the value at R of 525? You do not want to plug in 525 into that function.
Is it 523?
Let's see what it is. Tell me again.
Yeah, would it be 523?
Okay, let's see what happened here. I heard 523, Professor. It might be close to exactly.
Oh, but it wouldn't be exactly because of the ask.
And it's approximately 523. Is my graph way out there also close to the orange? And we name the orange this. So replace x by 525 here, not here. And you've got an approximation. Mr. Park,
Mm-hmm.
take this function for me, please. You may take it in that form there if you wish. And replace x by 525.
Mm.
See what you get. That's close to 523.
Um, 523.
Is it?
Yeah.
That's what we had.
Mm-hmm.
It's close to 523. So that's an approximation for R at 525. You want to use the orange oblique. Hey guys, I'm closing this down. Look at it closely. Let me throw in one more limit. Number 2.
Professor, Professor Ramsey, will you give us one of these on a test?
Of course. Limit as x is approaching, guys, let's approach -1, that's a vertical asymptote. Let's approach -1 from the right. That's my vertical asymptote. Now if I want that limit, that says you're standing on the right-hand side and you're coming in, you're getting close, like that. You're getting close to that -1. Coming in, getting close to -1. Question is, what is my function or graph doing? The closer I get to a -1, well, my graph's in black.
Negative infinity?
Is the black right here getting, dropping down like that when I get close to the red? Described as what? Negative infinity. They're doing calculus, except we're doing it on a graph. Maybe we should name this course calculus using graphs, something like that. That's what it is, calculus. I'm gonna step back and see if there's anything else. I think, guys, that might be enough right there right now. Okay, I'm leaving it. Are we okay? Yeah, Eric?
If you plugged in -525, would it be roughly equal to -527?
It would be, guarantee you. Good question, where I leave it. He said, Professor supposed to ask me to find this. R at -525. And where I do not want to go back and put in -525 into this. Just go to my oblique, it should be get close to the oblique also out there. So put it in here and get -527. The answer should be close to a -527. Eric, I think that's what you're saying, right?
Yeah.
Okay, it should be. Wow. Wow, wow, wow. Yes,
What section is this again?
this is, I guess it's on the handout there.
It doesn't say it, it just,
But, no, it's somewhere, I didn't? Okay.
it just says analyze.
Now you're gonna check the syllabus there and see what this was.
Okay.
It's in, chapter 3, last part, chapter 3.
Got it.
Yeah, Eric.
And then last thing, range, it looks like all real
Oh,
numbers.
let's get the range out of the way, I'm glad you brought that up. We got the domain out, I think, did we get the domain on this one?
No.
Okay, let's get both of them. Domain. Guys, here goes. X cannot be equal to,
-1.
I heard -1. And I see why we say -1 here, guys, where's my fucking all the way back here? So X cannot be equal to a -1, that's our domain. Now, since I have it graphed, let me say, Professor, what's this? Range the up and down, guys. Okay, describe for me the up and down on that black graph. I know it drops down through negative infinity. Now, how are you gonna describe, is it, I know it's getting close to the orange, but is it rising up as it does that?
Yeah, but it also does that on the left side. It
Does
shows
it,
that-
right on the left-hand side, is it negative infinity through positive infinity?
Yeah,
Yeah.
And there's no hole on the graph, is there?
no.
Thank goodness. There's my range. Yes,
So we're, I guess for the range, we are focusing on both, like both graphs, right, when we're determining.
well, if one graph does it for you, that's enough.
Okay, but in this case, like
In fact, it may have been easier to name the range on this piece here, cause it drops out forever.
Yeah, and then.
Goes out forever, so it's gotta be negative infinity or positive infinity.
Just making sure. I'm not
Yeah,
good at this.
whatever the other piece is doing, that makes no difference. Yeah.
What would the domain and, interval notation look like?
Where we say, where was it? X
Negative.
cannot be a -1,
-1.
something like this. Don't scare me.
That's it.
To infinity?
Yep.
Okay. Guys, me as a professor, unless I get a little time on Monday, I'm finished with rational functions. You see how lengthy they are? They are lengthy. Are we okay then?
Professor.
So,
It's like a 75% for me.
okay.
Professor?
It'll be 100% by the time you take that test next Friday. Okay. Yes, Vic?
Could you really quickly go over the division part of
The division, let me do this, sometimes this will help you. David, I'm glad you brought it up, hang on, where are we? Oh, I was trying to divide this into this, right? Oh, boy, here it goes. I did my long division, drew the little bar there, quotient, remainder, and all that stuff that you've heard back in the middle school. Okay, David, I wasn't gonna do this, but you asked. If you're clever, you can find what I'm looking for by using synthetic division rather than direct middle school division. Let me show you how to do it.
Yeah.
Okay, first you want to take your numerator, look at the coefficients. You got 1, -1, -12. That's the top part. And you're dividing that by x plus 1. Now here's the catch. You need a number to block off on the side if you're going to perform synthetic. You know how synthetic works. You have a number blocked off on the side and you start that little process. So I got to block off a number on the side here. Now that's the tricky part here. That's going to come from this. And guess what number I placed out there based on what I see here?
-1.
It is -1. Then you start, I'm getting all my little secrets away. Now you start doing this, like we did yesterday. Synthetic, 0, 1, product, -1, -2, product, 2, looks like a -10. I negative, did I do all that correctly, guys? Where am I? -12 plus 2, how do we get a remainder of 11 down here? Did I do that wrong?
So you then subtract the -12 in that
That was
long
the difference.
division.
That was
Oh,
the
and the
middle
long
school.
division?
Yeah.
That's
you
the
didn't
middle
break
school.
down.
That's the middle school.
You didn't get the final remainder in the.
Oh, that's a different.
No, that's a different problem.
Yeah, that's a
Oh,
different
that's something else I was pointing out.
Yeah.
That was your